Hello and welcome to this presentation related to the calculus. Here we're going to consider integration applications and specifically calculating areas and volumes of revolution. It is assumed you've reviewed previous presentations related to integration using standard forms or standard tables before reviewing the contents of this presentation. I'll briefly overview the presentation. This order is related to our workbook, so if you want to skip this, please feel free to do so. Initially, considering integration applications associated with areas. We'll derive the formula for calculating area. A is equal to the integral of y dx, integrated between the limits of a and b. So the present commences with a brief introduction outlining various applications, and also reviews the table of standard forms we'll be using within the integration process. Next, we review the calculating of areas under curves and consider calculation of net area and more often calculating the total area. We'll then consider example 1a. This calculates the area between the x-axis and the linear line y is equal to x plus 2. The limits over which the integration occurs is stated in the example. Then we have example 1b. We'll calculate the area under a sine wave between 0 and 360 degrees. Example 2a. We calculate the area between y is equal to 2x minus x squared and y is equal to x divided by 2. We need to sketch here the quadratic equation and the linear line, as where the intercept will form the limits of the integral. Exercise 1a, calculate the area between y is equal to x squared plus 2, that's a quadratic equation, and y is equal to 10 minus 2x, that's a linear line. Again, once we've sketched the equations, we'll find their intercept and find the limits over which to integrate. In question 1a, finding the area under the curve y is equal to 4 cos 3x between the limits of 0 and pi upon 6. Obviously that's a limit in radians. Question 2a, calculate the area between y is equal to x squared plus 3 and y is equal to 7 minus 3x. And again, we'll sketch the curve, determine their intercept, and find the limits of the integration process. And the final question related to areas is question 3a. This time we will calculate the area between three lines. That's y is equal to 3x, 2y is equal to x. We'll need to transpose that for y, of course. And y plus 2x is equal to 5. And again, we need to transpose that for y. If we sketch these three lines, we'll be able to find the intercept between them and then generate the appropriate integrals to calculate the area enclosed. And here are the approximate start times related to calculating areas. Just note that these times are rounded to the nearest minute. Let's consider integration applications, this time calculating the volume of revolution, acronym VOR. Initially, we'll derive the formula for volume of revolution. That's V is equal to pi multiplied by the integral of y squared dx. Notice y squared here, between the limits of 0 and b. Then we consider example 1v, finding the volume of revolution of y is equal to x plus 2 when revolved about the x-axis between limits of x is equal to 2, x is equal to 6. Question 1v, find the volume of revolution when the curve y is equal to 3 divided by x is revolved about the x-axis. And again, we're given the limits of the integral. And question 2v, find the volume of revolution between y multiplied by x and negative 2 is equal to 1 and y plus x squared is equal to 8. Again, we need to rearrange both of these equations in terms of y equals. But on sketching the two curves, we'll find where they intersect, and again, we will have the limits of the integration process. And here are the approximate start times for the volume of revolution section. Again, note these times are rounded to the nearest minute, but hopefully they will aid your ease of access through the presentation. Let's consider integration applications in overview. So within engineering, there are many applications of integral calculus. Examples include calculating areas, volumes, in electrical work, mean and RMS values, in mechanical engineering, calculating centroids of sections, in beams in bending, second moments of area, when considering rotating masses, calculating the radius of gyration, and there are many other applications of integral calculus. In this presentation, we'll just consider areas under curves and volumes of revolution. And here's some reference information. Table 1 here is the table of standard integrals. We referred to this table in our previous presentation where we introduced the integration process. And reference information continued. And I've restated the laws and the rules of indices in this table, as in some instances these will help us simplify the integrals we're going to solve. Okay, we're going to consider areas under curves here. And in figure 1 we're going to calculate the areas between A and B, between here and here. Now to do this we consider a thin elemental strip of height y and width dx. Dx is considered to be really thin. So the area of that strip, although it's actually a trapezium you can argue, because of the top of the strip has two points on the left and the right hand side of the strip at different heights. If dx is considered to be really thin, we can assume that's a rectangular strip of height y, which is the function of x, and width dx. So what we do with integration is we integrate that strip, that area strip, which is dA in this case, between the limits of a and b. So this integral here for area is equal to the integral of elemental strip dA between a and b. But a is actually a function of x, it's actually y the height times dx the width, integrated between a and b. Looking at figure 1 again here, if we now consider the area between a and d, what we notice is from the diagram is that between a and b we have a positive area, between b and c we have a negative area, and between c and d we're back to a positive area. If we performed an integral between the limits of a and d, what the integral would do is add up all the positive areas and take away the negative areas. So in other words, integrating directly between a and d gives us what's called the net area. If we want the total area, in other words the area between a and b added to the area between b and c added to the area between c and d, we need to split our integral down into 3 separate parts. In other words, we have to integrate the function of x with respect to x between a and b to get the positive area. We have to integrate the function of x with respect to x between b and c to get the area between b and c. But notice I made it negative outside here because I have a negative area. So the integral between b and c will give me a negative value. Multiply it by that negative outside, it will give me a positive value. So we'll add it up. The integral between c and d for the function of x there will calculate the positive area between c and d. So those 3 integrals in their format shown will actually work out the total area between a and d. Let's consider example 1a, which will help us illustrate the accuracy of the integration process. We're asked to calculate the area enclosed between the x-axis and the line y is equal to x plus 2 from x equals to 0 to x is equal to 10. So to plot the line y is equal to x plus 2, we've considered 3 coordinates, x equal to 0, x equal to 5 and x equal to 10. And for the given x value, we've calculated the associated y value. When x is 0, y is 2. When x is 10, y is equal to 12. The intermediate point at x equal to 5 is just a check that we have a linear line. Figure 2 here shows the line sketched. And the question wants us to calculate the area of the shaded region, outlined in yellow here. So initially, to calculate the area, we're going to use the standard formula. So area is equal to the base of our trapezium multiplied by the mean height. So the base is 10 units, that's along the x-axis. And to calculate the mean height, we simply add the minimum height, 2 units, to the maximum height, 12 units, and then divide by 2 to find the average or the mean height. So evaluating, the area shown shaded is 70 units squared.
If we now consider the same problem, but now we're going to use integration, what we would have to do is set up an integral between the limits of 0 and 10 for our function y equals x plus 2. So the integral of x plus 2 with respect to x between the limits of 0 and 10 will find the area under the line. This is a standard integral, going back to our standard tables, is ax to the n, and we know the solution for the ax to the n format. In this case we would ignore the plus c because we've got a definite integral. In other words, we have limits on our integral, we do not need to put the plus c after our solutions. So integrating x with respect to x, we get x squared upon 2 from standard forms, and integrating plus 2 with respect to x, we get plus 2x. Our limits are 0 and 10. Again, notice the format I have here. When I perform my integration, the integral sign is removed and I use square brackets to show the solution. All I do now is put the upper limit into the solution, so x squared upon 2 becomes 10 squared upon 2, and the 2 times x becomes 2 times 10. I then put my lower limit in this case the lower limit is 0, and all the terms in this case can go to 0. That's not always the situation, but it is in this case. Then doing the arithmetic on this, I end up with 50 plus 20 for my first bracket, so again I can show the area under the curve from integration is 70 units squared. Example 1b here shows a sine wave, so y this time is the function of x, it's the sine of x, and I've plotted it between 0 and 360 degrees. And what we're going to do now is find the total area under the curve. Now if I was to integrate directly between 0 and 360 degrees, I would find the area given would be 0, because the integral would actually add up the positive area and then take away the negative area. So if I want the total area under the curve, the sine curve between 0 and 360, I would need to break my integral into 2 separate integrals. Continue with example 1b here. We're going to now calculate the total area of the sine wave between 0 and 360 degrees, and I need to break the problem down into 2 separate integrals. So to find the area, my first integral will be of the sine x function with respect to x between the limits of 0 and 180. In other words, I'm working out the area under this part of the curve between 0 and 180. And I'm going to take away from that the integral of sine x with respect to x between the limits of 180 upon 360, but of course between 180 and 360 we have a negative area. We can see that clearly from the diagram, so the double negative there will mean we're adding up the areas. So all I do now is integrate my functions. Integrating sine x with respect to x gives me minus cos x. Don't forget sine ax is a standard function or a table, and that's between the limits of 0 and 180. If I now integrate the second function, integrating sine x with respect to x, again I get minus cos x, this time between 180 and 360, and of course I'm taking away the second integral. In other words, I'm ended up adding up my 2 integrals. All I do now is put my limits in. So in the first bracket, the first square bracket, I put the upper limit of 180 and I take away the lower limit of 0. And in my second bracket, I put in the upper limit of 360 and I take away the lower limit of 180. The rest of it is arithmetic, putting the numbers into the calculator. Just be careful here, I'm in degree mode, so degree mode on your calculator, and also be careful of the double negatives that are occurring in the solution here. You go through the arithmetic, you will find the area is actually 4 units squared. So the area under a sine curve, the total area between 0 and 360 is 4. Okay, example 2a here. We're asked to sketch the area of the segment cut off from the curve y equals 2x minus x squared by the line y equals a half of x. We're then asked to find the area of this segment between the limits of x equals to 0.5 and x equals to 1.5. So the first thing we need to do is to actually sketch the curves. So from curve sketching, we can see that we've got a quadratic curve. It's actually an inverted quadratic curve. It's a hat shape in this case. And we've got a linear line that cuts through the quadratic curve. Now, if you're not familiar with curve sketching, what you could do here is simply plot the points over, say, a range of, I've used x equals to 0 to 2 here, and then plot the equations y is a half x, y is 2x minus x squared on a diagram. You do need to have an initial sketch of these functions and so the shaded area you're trying to calculate. So to find the area, we're going to set up an integral. Now I'm going to have first of all my integral of 2x minus x squared with respect to x between the limits of 0.5 and 1.5. So basically what I'm doing here is I'm working the area under this curve here between the limits of 0.5 and 1.5, and that will find this total area here. So this area under the y is equal to 2x minus x squared equation is found from that first integral. I'm then going to take away from that the second integral, so I'm going to take away the integral of the x upon 2 with respect to x, again between the limits of 0.5 and 1.5. So what I'm doing now is integrating this line, the y equals a half x, between my 0.5 and 1.5, and I'm calculating this area, the area under the line, and I'm going to take it away from the yellow area to leave it with the shaded area. I would encourage you to think through what we've just reviewed here and clearly understand how the integral is set up. Clearly understand why the 2x minus x squared function is put before the x upon 2 function. It all relates to trying to find the shaded area in this question. Okay, example 2 continued. I've just repeated the formula for area from our previous slide. To me, that's the most difficult part of these questions, is coming up with the integral that we need to solve, in this case to find our shaded area on the graph. So now we're going to integrate both integrals here. We've got standard form ax to the n in both, so I'm just going to follow through that pattern. So taking the first integral, integrating 2x with respect to x, I get 2x to the 2 upon 2, and we take away from that x squared integrated with respect to x, that's x to 3 upon 3, between our limits of 0.5 and 1.5. What I've done on the second integral, I've actually taken this 2 outside the bracket before I integrate. It's just a factor there, so I can take that as minus 1 upon 2, it's a half of course. So I just integrated now x with respect to x, so that becomes x to 2 upon 2, again between my limits. Just tidying up in this next line, I've got 2x upon 2 divided by 2, so that simplifies to x squared with the 2's cancelling, minus my x to 3 upon 3 between my limits here, and on this last term here I've just taken the 2 from inside the bracket to outside the bracket, and that's how I get my minus 1 upon 4 and x squared in the bracket between 0.5 and 1.5 limits. The rest of it is just basically arithmetic. Here the next line, I'm now imposing my limits. In the first bracket I just put the upper limit in of 1.5 wherever I see an x, and I take away from that the lower limit, which is the 0.5 wherever I see an x, I put into the function, and then I take away my second term here, the 1 upon 4 is a factor outside, and I just put in the upper limit of 1.5 squared minus the lower limit of 0.5 squared. Okay, I'll let you look at the arithmetic. The answer there is 0.4167. Just for reference here, going back to the original integral on this slide, we could have actually brought the two integrals into one because the limits are the same on both integrals. They're both 0.5 to 1.5. So although I kept them separate integrals in this solution, we could have brought the minus x upon 2 inside the first integral and then simplified on like terms. I just mentioned this in passing here, as some of you may have noticed that, some of you may want to try that. But it's something to be aware of because it does simplify the number of integrals, although sometimes it complicates the algebra. In exercise 1A here, we're given some curves and we're supposed to sketch these curves. You'll see below I've got them drawn for us, but if you sketch them, y equals x squared plus 2 and y equals 10 minus 2x. If you didn't have the diagram there, we would have to sketch the actual curves. And the first one is a quadratic because it's an x squared term, and that will be a kind of bucket shape, and the second one is a linear line. That's actually the form c minus mx. It's a y equals mx plus c type of equation. So sometimes we're given these equations in the question, we actually have to sketch them or plot them out. In this case we've been given the functions here. One of the things we will need to find in this question is the limits of the integral. The question wants us to find the area enclosed by these two lines. So that means we actually need to find the limits of the integral. Now we can see from the diagram that the limit would be plus 2 on the right hand side, and it would be negative 4 on the left hand side. So we can get the limits just by looking at the diagram here, but in some questions without a diagram you would have to find what the limits are. If you did want to find the limits, if you didn't have the diagram on the previous slide, you need to find where the two lines intersect, because you're trying to find the area between these two lines. What we could do is equate the two equations, the x squared plus 2 equals to the 10 minus 2x. Rearrange them onto one side of the equation. In this case I've got a quadratic form of x squared plus 2x minus 8 equals to 0, and then you could solve that quadratic. I've solved it using factorization here to find that the x value is minus 4 and the x value is 2, so those are my limits. Another way you could do it, of course, is plot the curve, actually plot the equation if you want to. Okay, so what I've done here is try to find where my limits of the integral are, but from the previous slide we know that they're going to be at plus 2 and minus 4 by inspection. Exercise 1A continued here. I now need to derive my integral for the area between the two lines here. So looking at my diagram, I will find the area under this line first of all, between the limits of 2 and minus 4. So that's what I've got here. I'm integrating the 10 minus 2x line with respect to x between my limits. And then I'm going to take away the area under this line here, the quadratic curve. So I will take away then the integral of x squared plus 2 with respect to x, again between my limits. That will then give me the area between the lines. So on the next line I'm integrating the functions, they're all standard form here. Integrating 10 becomes 10x, integrating minus 2x becomes minus 2x squared upon 2, and that's between my limits of minus 4 and the plus 2. And I'm taking away my second integral, integrating x squared becomes x to 3 upon 3, integrating 2 becomes 2x again between my limits. And they're all standard form functions then. Okay, this next line is just evaluating the above integrals. I'm just putting the upper and lower limits into the square brackets. So taking the first square bracket, I get 10 times the 2, which is the upper limit. Take away, in this case, 2. I've noticed I've cancelled the 2's off on the above line. I've just used x squared here, so I get 2 squared. Take away my lower limit, so now it's 10 times the minus 4, the lower limit. Take away minus 4 squared. Just be careful of your directed numbers there, your negative sign. So that's the first square bracket dealt with. Now I take away my second square bracket, again, put in the upper limit of 2 in this case, so 2 cubed upon 3 plus 2 times 2, the 2 times x, and take away my lower limit, which is the minus 4, this time cubed upon 3 plus 2 times minus 4. The rest of it is basically arithmetic, but I encourage you to have a look at that and follow it through, and you end up with an answer of area is equal to 36 units squared. So solution to this question is the area enclosed between the lines is 36 units squared. Okay, this is exercise 1A. I'm just showing you an alternative solution here into the way we deal with our integrals. As I said previously, this is the area formula that's in two integrals. We've got the integral of the 10 minus 2x respect to x and the integral of the x squared plus 2 respect to x, but the limits on both integrals are the same. If the limits are the same, you can actually bring the two integrals together. So in this case, I could form one integral. And if you look at this, it's 10 minus 2x, take away my x squared. Notice I've got a negative here, that's why I'm taking away the x squared. And take away my 2 from the second integral. So I brought all the terms into one integral because the limits are the same. That's the key, the limits are the same. I can then simply tidy up inside that integral. 10 take away 2 gives me 8, and minus 2x minus x squared. So now I have one integral to solve with respect to x and not 2. So I'll leave you with that to consider if you like that solution. It does simplify the integration, but it does give you a little bit more algebra to deal with. If you follow it through, you get exactly the same answer, 36 units squared. Okay, question 1a here. We're asked to find the area enclosed by the curve y equals 4 cos 3x and the x-axis. And we're given some ordinates, these are basically the limits, of x equals 0 and pi upon 6. So they're obviously using radians here with the pi upon 6. Now the first thing we need to be aware of here is what does the shape of our curve that we're trying to find the area under look like? Because if it goes positive and negative, which of course it could do for a cosine curve, we need to be aware of that because of the signs. We go back to our original slides of this presentation. If we've got negative areas and we're trying to find the overall area, we have to account for that in our integral, otherwise we end up finding the net area. So we need to actually sketch out the waveform. So what I've done here is try to show one cycle of the waveform. We know that a cos waveform is 0 to 360 or 0 to 2 pi radians. So because we've got an omega value in the equation of 3, we can find the period of the waveform, the time it takes to do one cycle, by simply dividing, in this case, the 2 pi by the 3. So 2 pi upon 3 radians is the time period in this particular case. If we divide the 2 pi upon 3 by 2 to get half of that, we end up with 2 pi upon 6. And so half of that would be pi upon 6, 1 pi upon 6 if you like. And that's the limit we're given in the question. So from our sketch here, we can see that the actual area enclosed in the section we have to consider is all positive area. So we don't have to worry about the diagram going into the negative stage of that diagram. If you want to think that through in terms of degrees, then of course you would have 0 to 360 degrees for one waveform. If you divide that by 3, you would have 120 degrees. So the period of the waveform is not 2 pi upon 3 but 120 in degrees. If you half of that, you get 60 degrees, and if you half of that, you get 30 degrees. So the pi upon 6 is 30 degrees. Question 1a here, we now need to form our integral for area, and in this case it will be the integral of 4 cos 3x respect to x between the limits of 0 and pi upon 6. We know that that's all a positive area on our curve. Don't forget that cos ax is a standard function. It integrates to sine ax upon a. So in this case we will get an area equals to 4 sine 3x upon 3 between the limits of 0 and pi upon 6. All I'm doing the next line is putting in the limits. The upper limit is pi upon 6, so that goes into the equation, and the lower limit in this case is 0. We take one from the other. You'll find in this case the lower limit will end up becoming a value of 0. So we just got the upper limit to deal with here. Don't forget to be in radians mode here, because it's pi upon 6 we're dealing with. The angles are in radians, so you must be in radians mode for these calculations. Simplifying our function on the next line, we end up with 4 times the sine of pi upon 2. 3 divided by 6 gives me 2 there, divided by 3. And the area we find eventually is a 1 1/3 unit squared. Question 2a is a very similar solution to that we've already looked at in example 1a, so I would encourage you to stop the video here and have an attempt at this question. The functions are slightly different than used in example 1a, although the limits are exactly the same. The full solution is shown on the next few slides. Okay, full solution to question 2a is shown here. Again, the evaluation of the limits is as before in question 1a, just different functions we've used to plot this time. Question 2a continued. This is a graph of the two functions. Question 2a continued here. Don't forget in this question we are trying to find the area enclosed by the two lines we are given in this particular question, so we need to set up the integral appropriate to finding that area. In this case it will be the 7 minus 3x integrated with respect to x between our limits of -1 and 4, and we take away the x squared plus 3 integrated with respect to x between, again, the same limits. I've kept my integrals separate here when I've determined them, but you could bring them together if you wanted to into one integral because the limits are the same in both cases. I'll let you work through the slide to find the area of 20.833 units squared. Equation 3a here, we're asked to find the area enclosed by three straight lines here. The first one is y is equal to 3x, second one is 2y is equal to x, which we'll need to rearrange in a moment, and the third one is y plus 2x equal to 5. So one of the ways we could determine a diagram of this is perhaps to sketch the lines. So the first thing we need to do is put them in the form of, say, y equals mx plus c. So the first one is y is equal to 3x plus 0, where the m, the gradient of the equation, is 3, and the intercept with the y-axis is 0. In the second equation, just rearranging it slightly, the 2y is equal to x can be written as y is equal to x divided by 2 plus 0. Again, the y equals mx plus c format. The m is a half here, so a shallow gradient, and the y value, the intercept y value, is 0 again. And the last equation, the y plus 2x equals to 5, rearranged becomes y is equal to 5, take away 2x. So the m in this case, the gradient is actually -2, so negative gradient, and the constant, the y-intercept, is 5. So given this information, we could actually sketch the graph to the three lines. Question 3a continued here. Here is the graph of the three lines now. If you weren't able to sketch them, of course you could plot them, but basically what the three lines are showing us is this is the enclosed area that we have to consider and try and find the area between these three lines. So we're looking for the area inside of this triangle shape here. So the three equations we've got, y is equal to 3x, which is this line here, y is equal to x upon 2, which would be this line here, and then the negative gradient line, y is equal to 5 minus 2x, is this line here. Question 3a continued. So we need to set up an equation for the area that will find the area enclosed by these three lines. So what I've done here is put together three separate integrals to determine the enclosed area. My first integral is of 3x integrated with respect to x between the limits of 0 and 1. In other words, I'm considering this line over this length, and I'm finding the area under that line. I'm then going to add to that the integral of 5 minus 2x with respect to dx between the limits of 1 and 2. So now I'm looking at this line here between the limits of 1 and 2, and I'm finding the area under that line. Finally, I'm going to take away the integral of the x upon 2, the half x with respect to x, between the limits of 0 and 2. So what I'm doing now is taking away the area that's under this line to leave me with the area of the enclosed triangle there. I suggest you think that through as to how the equation there for area has been formed. Question 3 continued here. I've just repeated our formula for area that we derived on the previous slide with the three integrals. We're now going to evaluate all three integrals here. So the first one is integrating 3x with respect to x. So don't forget these are all standard forms, ax to the n. So that goes to 3x to the 2 upon 2 between our limits of 0 and 1. Then we integrate 5 minus 2x with respect to x. So that becomes 5x, take away 2x to the 2 upon 2. Between the limits of 1 and 2, and then we take away our final integral, which is x upon 2 integrated with respect to x, and that gives us x to the 2 upon 2 times 2 here between the limits of 0 and 2. What I'm doing here is slightly tidying up the integrals. The first one stays the same, so 3x to the 2 upon 2 between our limits of 0 and 1 is fine. I'm adding to that the 5x minus x squared between limits of 1 and 2. I just tied it up inside the bracket there. and then take away our x to 2 upon 4 between the limits of 0 and 2. Just tidying up our brackets there. Next line, we're just simply going to put the upper and lower limits into the equation to find area. So in the first square bracket, then we've got x is equal to a limit of 1, so 1 goes in, and we take away from that the lower limit, which is 0 in this case. So we can evaluate the first bracket. We're adding to that the second bracket with the upper limit is 2 going into the equation, and then we're taking away the lower limit, which is 1 in this case. So that's the second square bracket sorted. And then the final square bracket we're taking away, in this case the upper limit of 2 goes into the final square bracket, and we're taking away the lower limit of 0 in this case. So just put in the values into the square brackets here. The rest of it is evaluation. I'll leave you to sort the number crunching out. What you should find eventually when you work it through is that the area enclosed by those 3 lines is 2.5 units squared. Just going to show you this for question 3A, an alternative integral we could have used here. I've got 2 integrals here instead of the 3 we used on the previous page, but a little bit more complicated inside the integral. In this case, the area is defined as the 3x function take away x upon 2 between limits of 0 and 1. So what we're doing here is finding the area under this line, and we're taking away from it the area under this line between the limits of 0 and 1 here. And then my second integral I've got here is 5 take away 2x take away x upon 2 between the limits of 1 and 2. So I'm now looking at this line here, and I'm finding the area under this line between 1 and 2, and I'm taking away the area under this line, the minus x upon 2, between 1 and 2. So another variation on how to actually form the area integral that we could use. Okay, we will now consider volumes of revolution. This is another application of integration. We're going to start by considering our elemental strip again, as we did previously. Don't forget the elemental strip is thickness dx and height dy, where dx of course is really small dimension. In the previous work, multiplying the y by dx, we get the area of the elemental strip, and if we integrate that between our limits, we find the area under a curve. In this particular instance, we're going to consider the elemental strip to be revolved 360 degrees about the OX axis here. If we do that, we will get what's called a volume of revolution, and we'll get a very small cylinder of very thin thickness. If I want to work out the area of the end of a cylinder, I would use the pi r squared formula. In this case it would be pi y squared to find the area at the end. If I multiply that then by the thickness dx, I get the volume of a cylinder, a very small cylinder. We call that dV. Now if I integrate dV between limits of say 0 and b in this case, that's what's given in the question here, I would get the volume of the entire area of revolution. Don't forget dV from above is actually pi y squared dx, and if I take the pi outside because it's a constant, I end up with the integral of y squared dx between limits of 0 and b. And this is called the formula for volume of revolution. Example 1v shows us how we can apply the formula of volume of revolution here. What we're given here is an equation of a straight line, y equals x plus 2, which plots here. And we're asked to find the volume of revolution between x is equal to 2 and x is equal to 6. So what's the volume when that line is revolved through 360 degrees? So it gives us a kind of bucket shape, if you like. So our formula for volume is pi, the integral of y squared dx between the limits of 0 and b. Pi is the constant outside. In this particular case, the y function is x plus 2. Now what you need to be very careful of with the volume of revolution formula is that it's a squared function of x. So given that the y is equal to x plus 2, we are going to have to square that function before we can integrate it. But then we will integrate it with respect to x between our limits. So example 1v continued here. Here's our equation repeated for convenience. So the volume of this particular shape, pi, integral of x plus 2 all squared with respect to x between our limits of 2 and 6. Now don't forget then we have to square the bracket. The x plus 2 all squared must be squared before we do any integration. And don't forget that's a binomial bracket, so that's x plus 2 times x plus 2 when we say square it. So when we square x plus 2 all squared, we get x squared plus 4x plus 4. So that's the term we are going to integrate. So back to my volume formula, it's pi, the integral of x squared plus 4x plus 4, integrated with respect to x between the limits of 2 and 6. All standard forms now, x squared integrated gives me x to the 3 upon 3, plus 4x integrated gives me 4x to the 2 upon 2, plus 4 integrated gives me 4x. My limits are 2 and 6, and don't forget we must keep the pi, the constant, outside of the bracket. All I've done here is simplify, keep my pi outside the bracket, x to 3 upon 3 plus 2x squared, 4 divided by 2 gives me 2, plus my 4x between my limits of 2 and 6. Example 1v here. V is equal to pi outside my square brackets, and inside I get x cubed upon 3 plus 2x squared plus 4x are all the limits of 2 and 6. All we're going to do now is put those upper and lower limits into our bracket. So keeping the pi outside, put the upper limit in wherever I get an x. I put a 6 for my upper limit. We always take away the lower limit. Now wherever I get an x, I put a 2 for my lower limit, and I simply evaluate the function. I'll let you look at the arithmetic here. So we find that v is equal to 149 and a third pi, or 469.14 units cubed. Question 1v here, we're given a curve, function y is equal to 3 divided by x, or 3x to the minus 1. We're told the limits of this curve between x is 2 and x is 3, and we're asked to find the volume produced by the curve being revolved about the x-axis. So it's a volume of revolution problem here. So I plotted the curve, I plotted it from 1 to 7 here to give me a little view of the shape of the curve here, the 3 upon x curve, and we're asked to find the volume of revolution between the limits of 2 and 3. Question 1v continued here. So our volume formula is pi times the integral of y squared dx. In this particular case we've got y is equal to 3x to the minus 1. So again, don't forget, because the basic formula is y squared, the first thing we have to do is square the y term, which is 3x to the minus 1 here. So 3x to the minus 1 squared, that requires the third law of indices. If you go back to your indices, we'll find that gives us 9x to the minus 2. Again, let you think that through. The 3 squared is 9, and then the x to the minus 1 all squared from the third law will give you x to the minus 2. So our integral is actually of x to the minus 2 with respect to x between the limits of 2 and 3. I've just simply taken the 9 outside because that's a constant factor, so it can go outside with the pi. So when we integrate x to the minus 2, don't forget that's a standard form of ax to the n. Just be careful of your directed numbers there, but we end up with x to the minus 1 upon minus 1, or simply minus x to the minus 1. On the next line I've taken the minus outside again to be with the 9 pi. When you put your upper limit in 3, we get 3 to the minus 1, take away lower limit, 2 to the minus 1. The rest of it is arithmetic, and again I'll let you follow the arithmetic through. We eventually find that the v is 9 pi upon 6, or 1.5 pi. Okay, question 2v here. We're told that the area that's formed between two equations, the first one is y times x to the minus 2 equals to 1, and the second equation is y plus x squared is equal to 8. The area formed between them, when we roll through 360 degrees, forms a volume of revolution, and we've got to find the volume. Rearranging the equations given, so they're in a standard form here, the yx to the minus 2 equals to 1 can be rearranged for y is equal to x squared. In other words, divide both sides by x to the minus 2 and then bring the x to the minus 2 to the top on the right hand side, gives me y is equal to x squared. And then taking the second equation, just simply taking away x squared from both sides, gives me y is equal to 8 take away x squared. If I plot those curves, this is the y is equal to x squared curve here, and if I plot the 8 take away x squared curve, which would be this one here, I find that they cross between the limits of +2 and -2. Okay, so my limits of the integral here will be plus and minus 2 from the diagram. Okay, I need to derive my volume formula now. V for volume revolution. Don't forget volume of revolution is pi y squared dx integrated between our limits. So looking at the sketch here, I need to find the area under the y equals to 8 minus x squared expression between the limits of -2 and +2 first of all, and then I'm going to take away the area under the x squared term between the limits of -2 and +2. So writing that down in my integral then, I will get pi, the integral of 8 minus x squared, all squared, integrated with respect to x between limits of -2 and +2, and I take away from that pi, the integral of x squared, all squared, integrated with respect to x between limits of -2 and +2. So again, think that through as to how we derive that volume equation. Question 2v continued here. I just repeated the formula for volume for convenience. Don't forget what we're doing here. We're finding the area under the 8 minus x squared equation. So we're finding the area under this equation, first of all, between the limits of -2 and +2. And then we are taking away the area under the x squared equation. So taking the area under this equation away from it to leave us with that net area between the curves. And then, of course, we're revolving that through 360 degrees to find the volume of revolution. Now, with all volume of revolution questions, don't forget you have to square the functions, first of all, before you can integrate. That's very important here. So, taking the first integral, we've got 8 minus x squared, all squared. Don't forget it's a binomial bracket of 8 minus x squared times 8 minus x squared. So that gives you 64 minus 16x squared plus x to the 4. I'll let you check that for yourselves, and then take away our second integral. First of all, we've got to square the x squared, so third law of indices, we get x to the 4. From here on in, it's all standard integration, using our standard integration tables to do the integration. So keeping the pi's outside, don't forget, the pi's are constant. So 64 integrated is 64x minus 16x squared integrated minus 16x to 3 upon 3, and then the plus x to the 4 integrated plus x to the 5 upon 5 between my limits of -2 and +2, and then I take away pi times, then x to the 4 integrated is x to the 5 upon 5, again between limits of -2 and +2. Now I just impose my upper and lower limits into the various square brackets. So taking the first square bracket, I will put a 2 wherever I see an x for my upper limit, and I will put a -2 wherever I see an x for my lower limit. Don't forget, we're always taking away the limits here. It's always the upper limit, take away the lower limit. And then I'm looking at my second square bracket. I'm now taking away pi times, and then putting the upper limit in 2 x to the 5 for x to the 5 upon 5, and then I'm taking away -2 to the 5 upon 5. So again, just be careful of your number crunching, your arithmetic there. From there on in, it's just working out the values and ending up with a volume of 170 2/3 pi. Okay, looking at the summary of the presentation, we've looked at calculating areas under curves using integration. The integral of y dx between limits a, b has allowed us to calculate the areas under complicated curves. We do need to account for the signs though. If we have negative areas, we need to account for that within our integral. I've also looked at the volumes of revolution equation, pi integral of y squared respect to x between our limits of 0 and b in this case. And don't forget, with the y squared, you have to square the y function before you integrate. Bibliography stated for further information. Thank you for viewing.